Exercise 2.6. Find the range of the rational function y equals x squared plus 4x plus 3 divided by x squared plus x plus 1. Now we can see we can factorize the numerator into x plus 1 times x plus 3. And the denominator cannot be factorized. And we can see that the discriminant is going to be less than 0, so it is, if we had set it to 0, so there's going to be no values of x for which the denominator is equal to 0. Anyway, I was getting a bit ahead of myself. That's for sketching the function. For finding the range of it, it's pretty standard stuff. We just do what we normally do. So we got y minus 1 lots of x squared. This is just by multiplying both sides of the equation by x squared plus x plus 1. And then it's going to be plus y minus 4 lots of x, and then plus y minus 3 is equal to 0. And then if a value of y is going to be in the range of this function, that means there's going to be a value of x that is sent to it, which means the value of x makes this equation true, because this equation and this equation are equivalent to one another. And so we just need to check whether the discriminant, well, for what values of y is the discriminant greater than or equal to 0. So delta, our discriminant, is equal to y minus 4 squared minus 4 times y minus 1 times y minus 3. And we need this to be greater than or equal to 0. And this is just the working that requires expanding everything out. And we end up with the quadratic 3y squared minus 8y minus 4 needs to be less than or equal to 0. And if we solve 3y squared minus 8y minus 4 equals 0, we get that y equals 4 plus or minus the square root, 4 plus or minus 2 times the square root of 7 divided by 3. And then just rounding it in decimal form to get an idea of where it is. That's going to be 3.1, or you can say 3.10 to 3 significant figures, or negative 0.43 to 2 decimal places, I guess. So those are our, well, that's where this quadratic equals 0. And so if we're looking for all the values of y where the quadratic is below 0, so this quadratic right here, we can consider z equals 3y squared minus 8y minus 4, and then sketch a little parabola. So we know that z is going to intersect. So if this is the z-axis and this is the y-axis, we know that the parabola is going to intersect the y-axis at y equals 3.10 or negative 0.43. So it's going to look like that. And of course this equation here is, inequality here is equivalent to z less than or equal to 0, and we can see that that's precisely these values here. So for minus 2 square root of 7 divided by 3 less than or equal to less than or equal to y, less than or equal to 4 plus 2 square root of 7 divided by 3. So that is our range in exact form. So we can already see that when we sketch the graph of this thing, it's already going to be slightly different to the ones we've seen before, because we're only going to have y values between negative 0.43 and 3.10 approximately. So yeah. Alright, let's get into working out everything else we need to sketch the function. So we can already see that there are no vertical asymptotes because the x squared plus x plus 1 is never equal to 0. We can see that the x-intercepts where y equals 0, so x-intercepts where y equals 0 is when x equals -1 or -3. The y-intercept is when x equals 0, which is clearly y equals 3. We have a horizontal asymptote, that's just y equals 1, for reasons we've discussed multiple times before. Now for this one here, because we have the range of our function clearly trapped between two numbers here, it looks like there's going to be maximums and minimums. It's a completely continuous function because there's no vertical asymptotes, and it's a simplified rational function. So we should be able to draw the whole graph without taking our pen off the page everywhere. And so since it's stuck between 4 minus 2 square root of 7 over 3 and 4 plus 2 square root of 7 over 3, that's implying that it's gonna have, I guess, this kind of shape, with the line in the middle being the horizontal asymptote. Anyway, so let's do some calculations to find out where those where the maximum and minimum values are. So y prime is equal to 2x plus 4 times x squared plus x plus 1 minus 2x plus 1 times x squared plus 4x plus 3. And the whole thing is divided by the denominator squared. So x squared plus x plus 1 squared, but we don't care about that because we're just looking for the values where y prime is equal to 0. And I'll just go through it myself. I'm not going to make you watch this. Okay, so doing all the calculations, this is what you end up with. You end up with, we have stationary points where x is equal to 0.215 and -1.55. These are the exact values. And to find out which one goes with which, you can just stick them into the function and see what you get. But since one of these values was negative for the range, I think we had -0.43, clearly it has to be the negative number when you put it into this function, because if you put a positive value in x into here, you're going to get something positive. Right, so we can say that our maximum, so just adding to this list here, our maximum, or local maximum rather, actually I think, yeah, global maximum in this case. The maximum is when x is approximately 0.215 and y was equal to approximately 3.10, and the minimum is when x is equal to approximately -1.55 and y was equal to -0.43. And lastly, does the function actually intercept its horizontal asymptote? We can calculate that real quick. It looks like it's going to. Got to make sure we actually set it equal to its real horizontal asymptote and not like a y-intercept or something. So if it intercepts its horizontal asymptote, it just means that the function is going to be equal to 1 at that point. And so that can only happen if we have x squared plus 4x plus 3 equals x squared plus x plus 1. And then we can quickly get that 2x equals -2 which tells us that x is equal to -1. So our function intercepts the horizontal asymptote. So horizontal asymptote intercept is when x equals -1 and y equals +1. And of course we calculated our range to be between these values, so -0.43 less than or equal to y less than or equal to 3.10. When you're doing these kinds of questions in your exam, you should display all this working. So the examiner should know where you got these values from. It should be clear from your working where these numbers come from. And I think now we're ready to actually sketch this thing. So let's go ahead and do that. Okay, so here we go. Looking at all these details, we have a horizontal asymptote at y equals 1. Y equals 1. And we have x-intercepts at x equals -1 and -3. So -1 and -2, -3. And there's no vertical asymptotes. Plotting a couple of other points, we know there's a minimum when x is -1.55, so about there, and y equals -0.43. So that's going to be our minimum point, and we can label it as, well, what it is. -1.55, -0.43. And we're going to have a maximum when x is 0.0215, so over here, and y equals 3.10, so about here, I guess. Gotta be careful not to go too high. Alright, so that's going to be our maximum. So 0.215 and 3.10. And then what else do we have? We have a y-intercept at y equals 3, so about there. So 3. And does it intercept its asymptote? Yes, we calculated when x is equal to -1, y is equal to 1. That really doesn't look right, because I already said -1 is an x-intercept. Goodness me, that's embarrassing. Alright, let me go back and check my... Clearly, if I put -1 into here, I get 0. So let me go back and check my horizontal asymptote intersect calculation, which I believe was this part here. X squared plus 4x plus 3 equals x squared plus x plus 1. And then I subtracted x from 4x to get 2x. Brilliant. Genius level stuff right there. So actually x is equal to -2/3, not -1. My bad. Please don't disown me as your math teacher. I swear I kinda know what I'm doing sometimes. X equals -2/3, and y still equals 1, so I only need to cross out that part. X equals -2/3. Alright, so that's looking much better. So when x is equal to -2/3, that's when we intersect the asymptote. So -2/3 and 1. So that point there. Right, and then other than that, I think we're ready to go with this thing. It only intercepts the horizontal asymptote at this point here, so there's no other asymptote interceptions, and there's only 2 stationary points, so there can't be any other turning points. So that just immediately forces the shape to look like this. So we turn around up here, and we cut the y-axis at 3, and then we turn around at the top here, and then we come back down and we get closer and closer to the line. y equals 1 as we tend towards positive infinity or negative infinity. Just make it clear that this never actually touches the line.